Hello, I'm Evan, and this is a talk that I gave a couple of weeks ago for my candidacy exam for my PhD. So that's a stepping stone to talk about what I want to do for my dissertation. So what I want to do is in the field of Bayesian deep learning. This talk is going to be a bit of history and what I see as my way forward. All of this work is being advised by Sinead Williamson at UT Austin. So I'm going to go ahead and get started. And my goal, I guess, is to show to anyone, and particularly a less familiar, less statistically literate audience, what I'm working on. That's my goal. I don't know if I'll succeed, because it's the same talk that I gave for my exam. But let's get started. So I'm going to talk about neural networks. And if you've studied them at all, it'll be review. If you haven't, that's okay. I'll talk about them. And then we'll talk about Bayesian neural networks, so adding Bayesian inference to neural networks. Then talk about some of the work that I've already done and some of the work that I hope to do. So this is a perceptron. We're going to build a neural network kind of from the ground up. So a perceptron is a pretty simple idea, and basically it's something that takes some input, it's x over on the left, and then produces some output over on the right. And the way it does that is it takes a weighted sum of the inputs. So maybe for our input, maybe we'll have income and a house's square footage and their property tax, whatever it is. And I'll take a weighted sum of all of those. So those weights could be positive, they could be negative, they could be really large, they could be very, very small. Add them all up, and then apply some activation function. So we'll talk a little bit about a few options later, but it's just something to where maybe I don't want just the weighted sum, maybe I want to transform it somehow. Maybe I only want positive values, maybe I only want values between 0 and 1, but this is kind of analogous to how a neuron works in the human brain and the brains in general. Of each neuron gets input from several other neurons, those would be our input x's, and has different strengths of connections to each one, does some processing, and then either fires or doesn't fire. We're going to be a little bit more flexible about what our output looks like, so instead of just a 0 or a 1 for firing and not firing, maybe we want something else. So a neural network, one of the simplest versions is the multi-layer perceptron. And it's really just a bunch of these perceptrons all hooked together. So here we have 4 inputs, we have 4 perceptrons in the first layer, 2 in the next, and so on. Where each of these lines, each of these arrows, represents doing a weight. So we have, for the first perceptron in the first layer, we have some weighted sum of our input. And then for the second, we have a different weighted sum, so different weights. And we could, in principle, apply different activation functions at each layer for each node, each perceptron. I kind of use neuron, node, and perceptron interchangeably. They all mean the same thing. But this is really all a neural network is I have some inputs, I have some structure that I've made of a bunch of perceptrons, and I produce some output. And my goal is, given some data set, some covariates, some input that I have, I'd like to make some kind of prediction. So maybe I'm trying to predict someone's income from information I got from their resume, or maybe I'm trying to predict where another car is on the road based on an image. Or maybe I'm trying to figure out what is in an image in different places. Or maybe just the whole image, what's an object in it. Lots of different problems that we could solve here. I'm not going to go into a lot of detail, but I'll give a couple examples in just a minute. So, it's a little bit of math here. Don't worry, there's not a lot of math in this talk if math scares you. So as a statistician or a computer scientist, one of the things that I need to know is, so I have this model, with all of these different weights. Well, how do I know what the right weights are in all of these little weighted sums in my neural network? And the answer is typically backpropagation. So what backpropagation is trying to do is minimize some cost function. So in regression, what this does is, let's say I'm trying to predict someone's income. So their real income observed is Y. I have some other information about them, X. And the output is this in X condition on W, so all of my weights. And so the double bars, the 2, 2, that is really just saying, in this particular case, take the square. So I want to minimize the square difference between the real income and what I predict is their income. So if I do this for a lot of people, I might be able to learn, based on their resume, what their income is, for example. That kind of a thing. And so by minimizing that difference, that means that whatever the neural network says and whatever is true are going to get closer and closer together for everybody. And we could do a similar thing for classification. So the classification is a slightly different problem, but basically it's saying, trying to put people into different classes, or put our input into different classes. So this could be images as our input X, and we might be predicting whether it's a cat or a dog, or a cat or a dog or a fish. That kind of a thing. So we're trying to put some probability on how likely is this to be a cat, how likely is this to be a dog, and so forth. Okay, so those are the kinds of problems that we're solving with neural networks. Some additional things we could do, we can add some regularization, which basically just means that I want to constrain the weights a little bit. We'll talk about why I might want to do that in a minute, but if I add this first one, this L1 loss on the regularization for the weights, then I can actually induce some sparsity. So some of my weights in the model would be exactly 0. Otherwise, if I do the squared loss, so the W squared, then I'm not going to get sparsity, but I will get shrinkage, so it reduces the values of the weights a little bit. And this generally means that my network will be more robust. So when I go from the data I have to wanting to predict on some new data, I'm going to probably be in a better place. My predictions will probably be a little bit better. They won't have issues. And backpropagation, if you're not a math person or not interested in how it works, you can tune out for a second. But the basic idea is that it follows the chain rule for derivatives and keeps track of quantities that we've already computed. So here on the right at the top there, I have y equals 1 over 1 plus e to the minus x. So based on some value x, I can compute y. And then based on some value y, I can compute z. Okay, so that's what I would do on if I'm trying to get the output z from my input x, that's what I would do. I can compute y and then I compute z. Well, when I want to go and do backpropagation, I need to use the chain rule. So here I have this partial, the dz by dy, is just actually minus z. I can rewrite it that way. So the derivative of z with respect to y is actually just minus something I've already computed, which is z. And then similarly, I can go down one step further and take dy by dx, and it turns out that derivative of y with respect to x is really y times 1 minus y. This is really just what makes backpropagation helpful and fast, is that I can usually get away with only keeping, if I can remember all the values that I computed to try to produce the output, I can take the derivatives very quickly and based on information that I already have. So it doesn't add a lot of computational effort to take the derivatives, which I need in order to learn what the best weights are. Okay, so a deep neural network is really just a neural network with a lot of layers in it. That's all deep means. It doesn't have a deep, I made a pun, meaning. So why are they good? So one, like I said, they're fast, they're relatively flexible. I can do stochastic gradient descent with backpropagation, so that's just meaning I can take a few examples out of my data set at a time and take a few steps, learn what's best for that bit of my data, and then try another batch of data, and keep going, and I'll eventually arrive at good results for my weights. And neural networks have this kind of unreasonable effectiveness. You can generally, for various problems, attain very high accuracy and precision and recall. For example, these 3 papers here, they're all based on the same structure of a network that was developed in this first paper. That's by Google, primarily. And that is trying to solve the ImageNet problem. I'll talk about ImageNet specifically later, but basically you can think of it as trying to identify, oh, this is a cat, this is a restaurant, from an image. And it did so better than any technique before it, but it does so at least as well as a human would be able to judge the objects in the images, if not better. And then that same architecture, that same structure of network with slightly different weights, was used to detect melanomas from pictures. So something that you could even take with your smartphone. You could take a picture of a skin lesion and it would tell you whether it's malignant and has cancer, skin cancer, melanoma, or whether it's benign. And that did so exactly on par with 21 board-certified dermatologists. So that's expert level accuracy. And then, again, same kind of story for chest x-rays detecting tuberculosis. It did so with just phenomenal sensitivity and specificity. Those are particular measures. Sensitivity of like 97%, specificity of 100%. It means basically 0 false positives and false negatives. Like it's just tremendous and expert level. So, have we solved all data ever? Is statistics over with? Well, not really. So, neural networks have some drawbacks. One is that with this format that I've just described, we really only get a point estimate. So if I'm trying to predict someone's income based on some information, like their resume or something, I'm going to get some pretty particular guess at their income. So I might guess that they're making $37,422.63. I mean, maybe that's exactly what they are, but that doesn't seem like a reasonable kind of guess to make. I don't have any notion of uncertainty in that prediction. So instead, I'm just getting some number, and I'm hoping that it's close, whatever close means. They also have neural networks have a tendency for overfitting. So this kind of comes from this problem of, in a deep neural network with lots and lots and lots and lots of nodes, lots of perceptrons, that means even more weights. And sometimes there's just so many weights that I can start basically memorizing all the information I've seen and not be able to generalize very well. To give this some context, that first paper up there, the one that can identify objects and images, that model has 6.8 million parameters to learn. So that's all the weights and a few other things, mainly weights. And this big, large-scale, big data set has 1 million images. So for 1 million examples of data, I have 6.8 million parameters that I need to learn. So I kind of have like 6.8 parameters per image, sort of. It doesn't quite, the simplistic understanding doesn't quite work there, but it does mean that I really could start overfitting very easily. And there's also this problem of not really having a clear choice of structure in the network. Should I have 4 layers or 5? Should each layer have 5 neurons, or should it have 500? And I can try a bunch of things and see what works, but it's usually not something principled. So we're going to address these to some extent anyway. Okay. So when I want to jump from Bayesian neural network, from backpropagation and standard neural networks to Bayesian neural networks, I'm going to make a couple of changes. So whereas before I had a cost function, so if you'll remember, like y minus whatever my guess is, the whole squared, I'm going to have a probability model. So I'm going to define a likelihood for regression. Maybe I use a normal distribution, a bell curve, where whatever I'm predicting for the income is normally distributed, where the center is whatever my neural network says, and maybe I have some noise. So maybe it's a very small amount of noise, maybe it's large, but that's basically I'm predicting a bell curve, so I have some notion of uncertainty for my prediction, rather than just a particular value. I can do the same kind of thing with classification with a categorical distribution, so that's like, well, there's a 97% chance it's a cat, and a 30% or a 3% chance it's a dog, and so forth. What Bayesian statistics does is I'm going to add what's called a prior distribution. So the frequentist statistics, which is what all I've talked about before does, assumes that there's one right answer, but we just don't know what it is. So each weight has one exact value that would be perfect, but we just may not be able to figure it out exactly. In Bayesian statistics, we're going to assume that our weights are actually random. So it's a little weird, but that's okay. It's a model, and it's one that works very well. In some cases, it actually makes more sense than frequentist statistics. So we might start off by saying, like, well, I really think my weights should be distributed by a normal distribution that's centered at 0. So I think my weights should be mostly around 0 with some variance. Or maybe my weights, at each layer, I expect there to be some correlation. So all the weights that are connected to a particular input should be kind of similar. All the ones with a particular output neuron are kind of similar, that kind of a thing. And so Bayesian statistics, all we need to do is, the goal is to compute what's called the posterior distribution. So we just apply Bayes' rule, and yeah, I need an integral, and if you haven't done calculus for a while, those symbols might not make any sense, but that's okay. The basic idea is I'm going to combine my prior distribution and my likelihood, and I want to be able to incorporate information from the prior, incorporate information from my data, and use that to form this updated belief about, in this case, theta, all of my parameters. So based on all my data, what do I believe all of my weights should be? So maybe based on my data and this prior distribution, well, maybe my data didn't tell me much, so the posterior distribution should look a lot like the prior. Or maybe my data told me a lot and my prior wasn't very good, And so I really need to change what I think my weights look like. So in principle, relatively straightforward, but the problem is, in this case, because the neural network is just so complicated and so nonlinear, with all of those activation functions and all the layers, computing that denominator of that fraction, that integral there, is actually really intractable, just not possible. And really, even if sometimes I might be able to get away without computing that directly, but I can't do what I want to do. I can't really go forward straightforwardly. So I am going to talk about a couple of different options in the literature for how to do Bayesian inference, so doing things with this posterior distribution for neural networks. Yeah, so like I said, if we could compute the posterior, then we'd be great, we'd be done, I'd be working on a different problem. But it's not possible in this setting. We can do MCMC, so this is Markov chain Monte Carlo, so basically do simulations, and we can end up taking a simulation from the posterior distribution without having to compute stuff analytically. So we can basically get an empirical sample and work with that. And this was done with a technique called Hamiltonian Monte Carlo in 1993 for Bayesian neural networks by Radford Neal. If you happen to be a physics person watching this, Hamiltonian is physics Hamiltonian. It's an interesting technique. Highly recommend it. Not going to talk about it today. The problem with MCMC is basically I just have to run this simulation thing for a long time in order to get anything reasonable. And with 6.8 million parameters maybe in my model, I'm just going to have to run this thing for a long time, and probably longer than I care to do. It might be days or weeks or months or years of computation time in order to really get a good sample from the posterior distribution. So, if I can't do things analytically, so that's just with math, which I can't, and I can't really do MCMC, which would be great, but it just takes forever, I need to do something else. So, what we have are approximate methods. I'm going to talk about three of them: assumed density filtering, the Laplace approximation, and variational inference. But there's all kinds of methods that have been tried on neural networks, but these are kind of three fundamental sort of ideas that are interesting and widely used. So the Laplace approximation is an old idea, but applying it to neural networks is relatively new, dates back to 1992. And the basic idea, if you're familiar with a Taylor approximation, it's just a second-order Taylor approximation. If you're not, that's okay. Basically what I'm doing, we can look at this picture down here. So this this distribution with the two peaks is my true distribution, for example. It's a Gaussian mixture model. And this MAP line is the maximum a posteriori. So this is the point at which the posterior distribution is maximum. And all this Laplace approximation does is it looks at the curvature of the distribution at that point. So like how quickly is it accelerating, as it were. And if it's accelerating a lot or accelerating very little. I'm using accelerating as a physics term because that's maybe a little bit more familiar. And I'm going to basically use that curvature, that sort of acceleration, as to define the variance of a normal distribution. This falls out of the mathematics of the Laplace approximation, It's like I said there, it's locally quadratic, and it turns out that forms a Gaussian. And so this blue dashed line is what you get if you do the Laplace approximation for this simple distribution. So we got the peak in the right spot for the main peak, but we've captured some bit of the variance of the distribution. Hard to really say whether this is the best way to approximate the distribution with a Gaussian, but it's certainly reasonable. The main problem with the Laplace approximation for Bayesian neural networks is that in order to get a really good approximation, I need the Hessian. So this is not just the second derivative in one dimension, but in each dimension with respect to each other dimension. And so this forms a matrix, we call it the Hessian. And the problem here is that, thinking back to this same example of 6.8 million parameters for this big Google architecture, the Hessian would have 46 trillion entries and take up like 145 terabytes of memory. So I don't know about you, but I think even Google might even say, yeah, that's too much data for just one little object that I have to update all the time. That's a really gigantic thing to work with. And we can make approximations to that, even so we make an approximation on top of an approximation, and it turns out a lot of the easy approximations just don't give us the kind of information we'd really like. And one of the reasons is, basically, if the peak of this distribution is just like a little bit more sharp, that radically can change my approximation, whereas it really shouldn't. Like I might really get a much larger or much narrower variance in my blue dash distribution based on just a tiny change in the peak. So that's not great. And if I had the full Hessian, I could account for that, but in practice, that's just too much data. Okay, so this is like one of the first attempts. Pretty good, but has some problems. Variational inference is another thing we can do with Bayesian neural networks. The idea here is we kind of squint at the distribution. So whatever our true distribution should be, we're going to have a variational family of distributions. So, for example, we might take a normal distribution, which is what I've done below, with some mean and some variance that we need to fit. And basically, all variational inference does is say, hey, I want to, whatever my distribution looks like, the true one, I'm going to approximate it with a Gaussian, and the way I tell what the best Gaussian is to do that is by some distance that's defined on probability distributions. So in this case, we'll use the KL divergence. It's not a distance, but it kind of is like a distance. And it's just something that says, if I give it two distributions, are they really close to each other? Are they really far? And I can optimize that. So I can change the mean of my normal distribution until I get that right. I can change the variance until I minimize the distance between the distributions. And so that's what this looks like in the figure below. So this is minimizing the KL divergence between my approximation, the variational distribution Q, and the true distribution P. So we recover something that looks kind of like the Laplace approximation on the previous slide, but it's a little sharper. Variational inference tends to underestimate variance. So just kind of by the formulation, it likes putting most of the mass of the approximation where most of the probability mass is of my true distribution. And I believe the first paper to apply variational inference to Bayesian neural networks is this one in 2011. One problem it has is that there's still an MCMC step, so we can do a lot more computationally than just doing straight MCMC for the whole problem, but I still have to do this step and still have to do some sampling. This is updated more recently in a paper called Weight Uncertainty in Neural Networks that developed the Bayes by backprop algorithm. That came up in the discussion after my talk. But it's still a very similar idea, and still there's some step where we have to do MCMC, where we have to run a simulation to get some samples and work with that. And that just adds some computation time, which I'd rather not do. I'd rather be able to drop these in, like whatever Bayesian solution we come up with, I'd rather be able to drop it in for existing solutions and not have to pay a tremendous computational speed penalty. I just don't think that in practice people will go for something that's more correct, and has some uncertainty, but is 10 times slower or 100 times slower. I just don't think that's a reasonable assumption to make. I'd rather have something practical. And then maybe if we sell them on good estimates of uncertainty, then eventually maybe we want to move that direction. Okay, that's personal note, and why I don't like the MCMC likelihood for variational inference. Okay. So another method, and this is the one that we're going to focus on that we can use for Bayesian neural networks, is called assumed density filtering. Conceptually, it feels pretty similar to variational inference, but it is different. I won't blame you if you want to think about them pretty similarly, though. So we're again going to have some variational, well, not a variational distribution, but an approximate posterior Q, and it's going to have some known form. So maybe, again, we might take a Gaussian, maybe we take something else. And the basic idea here is I'm going to make one step. So I'm going to see one new data point. I'm going to write down the exact posterior. So for the first step, it will be the exact posterior. And then I'm going to project that posterior back into my family. So it's the same kind of idea in variational inference, where I'm trying to find the best approximate distribution out of my family of distributions, so the best mean and variance for a normal that approximates whatever posterior distribution is true. There's a little bit of more of a lie in assumed density filtering, so I'm going to use my existing approximation of the posterior Q in order to form my new P theta given yt plus 1. So this is that's why the exact is in quotes there. The idea is if we've matched the shape of the distribution well so far, so we've looked at 10 data points and we've done a pretty good job with our approximation compared to what it should really be, then I can reasonably take one more step and be okay. So that's the assumed density. We're making sequential steps here. And then the projection is the same kind of thing as in variational inference, where I'm taking the approximation and finding the best version of that approximation, the best parameters, to explain this new almost exact posterior. And in the original paper, this is given as, again, a distance between two probability measures. Distance measured between two probability distributions, I should say. But we'll end up using the KL divergence, but with swapped. We'll use the KL divergence, but with swapped order. And so that actually looks a little bit different. So the KL divergence isn't symmetric. If I put P and then Q, or Q and then P, it actually, the best version, the best distribution is different. So the dashed black line is what we had before. So that's when my approximate distribution is the first parameter. If I switch them, it turns out for the normal distribution in particular that the location parameter of the normal, where the center is, should be exactly the mean of my distribution P, and the variance parameter of the distribution should be exactly the variance of the distribution P. So all I want to do in this case is moment matching. So whatever the mean is, I should have the same mean. That's not true if I swap. I think I said swipped because I was trying to say swapped and flipped. That's what happened. If I put Q first, then I'm not doing that same thing. I'm putting most of my distribution where most of the other distribution is, but I'm definitely not matching the mean to the mean of the other distribution, so forth. Okay. So the technique that I've been working with is called probabilistic backpropagation, and Miguel Hernandez Lobato is actually on my committee, that's kind of cool. So probabilistic backpropagation is primarily using assumed density filtering, that technique we just talked about, but applying that specifically to Bayesian neural networks. And the particular model looks something like this, where my prior on all my weights is an independent normal. My approximate posterior on each weight is an independent normal distribution. So I'm going to learn a mean and a variance for each weight. And then I'm only going to talk about regression. That's what they talked about in their paper, but we'll talk more later. And the beauty here is to get around the MCMC, so to try to compute the posterior predictive. So that's a fancy way of saying if I look at all my data, and then I look at some new data point, what should my distribution be for that data point? So given all my information, what's the information about the next one? The beauty here, normally we would have to do MCMC to sample around all of the distributions for my weights and get some kind of distribution for my prediction. But instead, we're going to make a bunch of closed form approximations. Okay, so here's what that looks like in practice. So let's say we're somewhere in the middle of my neural network. Let's say at this particular point, I have exactly one input and exactly one output. So I just have one x, and I'm trying to compute through a perceptron what the distribution should look like on the other side. And let's, just for sake of argument, say that I've modeled the distribution well so far by a normal distribution. So we have x here with a mean of 3 and a variance of 2.25. That's what that looks like. So if I multiply my x's by a weight, what should that distribution look like? Well, it looks kind of like a normal distribution. It's not actually analytically a normal distribution, but in the gray, in the top right figure, you can see roughly what that looks like, and the red is what we're going to make as our approximation. So we've missed the peak a little bit. Our approximation, that's just a Gaussian with the same mean and variance as the true distribution. We didn't quite capture the peak, but that's okay. Then we apply an activation function. So this is on the bottom left is the ReLU activation, rectified linear unit. It's 0 for any input less than 0, and it's just the same value as the input if it's greater than 0. So when I apply that transformation to this combined distribution of x and w, that multiply, then I get what's at the bottom right. So if we look at the histogram there, the gray bars, We don't get any values less than 0. We have some values that are exactly 0. And then we kind of have this truncated distribution that if the XW distribution was normal, then I should have analytically a spike at exactly 0 and a truncated normal distribution. That's the analytic solution there. And so we kind of can see that. So we have something that looks kind of like a bell curve that's been cut off at 0. But I'm going to go ahead and approximate it with a normal distribution. So I'm not going to pay attention to the fact that I really shouldn't have any values less than 0. I'm just going to go anyway. But this is the kind of approximation that we make. And we'll do this over and over for each layer of our network in order to make a prediction about our response variable y. And so mathematically what I'm doing is I'm continually matching a mean and a variance at each layer, so that at the last layer, ZL, I'm assuming that it's normally distributed, and then my y is normally distributed around that. So this is an approximation, because in reality, what I should do is say that y is really centered around the output of the network given some sample of weights with some variance. And I should sample a bunch of weights over and over and over and over and over again in order to really understand what that distribution looks like. But by making this approximation, I can do this all really fast. And it turns out that my results are pretty good. So if we look below this figure, the PBP is what we're looking at. The HMC to the top right is Hamiltonian Monte Carlo, and this is kind of the ground truth. It's described it as the gold standard for this problem for a Bayesian neural network. So that's like the best understanding that we have with a neural network model of what that data should look like. And probabilistic backpropagation seems to really do well. It captures almost all the same kinds of features as Hamiltonian Monte Carlo did. Below on the bottom left is variational inference. So that left a lot to be desired in this particular example. And then we have standard backpropagation, so no uncertainty, but probabilistic backpropagation seems to get basically modeled the same function. So the mean there, that gray line, seems to be basically identical, at least to my eye, as what we'd get with standard backpropagation. So we've basically gotten the best of both worlds here. So we've gotten something that gives us the same result of standard neural network for the mean, and we've captured uncertainty just about as well as the slow, correct, exact Monte Carlo method. That's great. And the algorithm is fast. The updates to the weights, so when I see a new data point, I go and relearn the parameters for all of the weights. But all of that works just about as fast as standard backpropagation. There's twice as many parameters compared to a standard model of the same structure, but it's fast. It's even been extended to binary classification with simple transformation, but multi-class classification, so this is when I'm trying to determine, is this a dog or a cat or a fish or some other thing? I have to do MCMC, which again, I don't like that because it slows things down. Okay. So here's a brief comparison of all the different kinds of techniques that we might use. So this is MCMC, so that's the exact but slow solution. Variational inference, which is kind of a medium speed, but definitely faster than MCMC. And then all the way on the right, probabilistic backpropagation, that is all closed form, making a lot of approximations. So just to compare, like with MCMC, we're always keeping track of exactly weights, whereas in variational inference and probabilistic backpropagation, we're keeping a distribution on the weights. So we don't care about a particular value of the weights in those algorithms, as compared with MCMC, where we do have a particular value at all times. And yeah, and so MCMC probably is not going to work very well at scale, so lots of a really deep network, lots and lots of data, and the speed is going to not work at all. Versus probabilistic backpropagation, yes, we've made a lot of approximations along the way, but it's going to work for a lot of data, and it's going to work quickly. Okay, so moving on to what I've been working on. So the first thing I did was I re-implemented the probabilistic backpropagation algorithm just to make sure I understand the paper. But then I started thinking about different activation functions. So the original paper only uses that bottom one, the ReLU. And it's fairly common in the literature, but it's not the only function that's used. The sigmoid is common, hyperbolic tangent, other functions are relatively common. And one thing that we can do, at the risk of making a very poor distributional approximation, we can actually use a step function. So the theory for neural networks, at least the biological basis, maybe not the theory, but the biological basis for neural networks is really a 0 or 1 sort of operation. The neuron is firing or it is not firing. And traditional neural networks can't really use a step function because it's flat everywhere except for a discontinuity, and taking the derivative of that, so finding the slope is 0 everywhere, and it's essentially infinity in one spot, and that's just not helpful. So in probabilistic backpropagation, though, if all I want is the mean and variance, I can do that. I can keep that. So I just thought it might have some interesting properties, even though using a normal distribution to approximate the result of that step, which would be a spike at exactly 0 and a spike at exactly 1, using a nice continuous normal distribution for that is not really the best idea, but it would work, and so I was interested to see what would happen. And this work really just led into thinking about the approximations that we make in probabilistic backpropagation. So a similar setup as before, slightly different distributions for x and w. And here we see there is a much larger spike at 0 for x times w that we're just not capturing at all with a normal distribution. And so if we use, say, the sigmoid and apply that, the normal distribution approximation in the on the bottom right is okay. We miss the peak, but the rest of it is like okay. The actual values can only range from 0 to 1, and our variance is a little bit bigger, but that's okay. Problem is, if we change it again with not a lot different, at least to the eye, we might end up with a bimodal distribution, and our best approximation for that bottom right down there is really bad. That red line down there is our Gaussian that we're trying to approximate. And so that leaves a lot to be desired. And that's not just a problem with sigmoids, it's a problem with the ReLU also. So we have something here that, like, most of the samples from this distribution are at exactly 0 for the bottom right, but just a little bit is kind of positive. So that would be the tail of something like a normal distribution, but we're trying to approximate that with the whole thing with a normal distribution and kind of missing all of it. So one of the questions that this brought up was, well, what if we use a spike and slab? So that's what's written below, and basically that just means, what if I use a mixture of a distribution of a exactly 0 plus a normal distribution? So I still am ignoring the in this particular case, there's no value in the f of xw that's less than 0. But I'll ignore that. But I will try to capture all of the probability that should be exactly 0. And then I'll smoothly capture the rest of it as a normal distribution. So this is a spike and slab is what this is typically called. And this is something that I'm working on. I'm working on it for the forward pass like this is talking about, where we have our input and our weights. We can multiply those together, then we apply an activation function, and continually keeping a spike and slab approximation for each of those. For like the x, which is the input, which becomes an output, which becomes the input for the next layer, which becomes the output of that layer, which becomes the input for the next layer. We can also do that for the weights, though. So we could have weights that are exactly 0 or normally distributed. So that's what I'm working on, is being able to learn some sparsity on the weights using a spike and slab, and keep that notion of sparsity all throughout our predictions so that at the very end, when we're making a prediction, we might have a prediction of exactly 0, or we could have something that's more normally distributed, or we have a blend of the two. That's the big idea, but still working on it. Some other things that I plan to do are really just to add tools in the toolbox for probabilistic backpropagation. There are a lot of tools in standard neural networks that we don't have right now for probabilistic backpropagation. So one is trying to replace what's normally done for classification. So, like I said before, probabilistic backpropagation can do multi-class classification, but requires MCMC to do so. So that's that first one, that p hat, that's how they do it. And in order to get a distribution for p hat, they take a bunch of samples for x, which is normally distributed, and get the resultant distribution. And we're wondering, maybe we can do something else. Maybe we can do something by dividing space into regions. So whatever our neural network predicts, we then go and see which class is it closest to. So our output is normally distributed, or a spike and slab type of thing, but normally distributed. And we go and look at a region and see how much of the probability mass is in each region. But again, I haven't started work on this other than just a very brief sketch. Another thing that's really common, especially for images, is called pooling. And the most common is max pooling. And just a quick demonstration of what that looks like is below, where we take patches and we need the maximum of each patch. This is a very trivial operation for standard neural networks, but for us we need a distribution of the maximum of a bunch of variables. And because the variables are normally distributed, that's not trivial. So this is actually a very big problem, one that's not addressed very well, but the hope is to work on that, come up with some reasonable approximations, and be able to use pooling, be able to use convolutional layers, be able to apply probabilistic backpropagation to images a lot more easily and with a lot better results than what we can right now. This is one of the final things that I want to do and look into, is the idea of transfer learning. So this is a very common practice in standard neural networks, where we have some data set, but we don't have many examples. So in this case, this is the bottom row, the OASIS data set. Has 434 MRI scans. And there's a lot we could try to learn from that, but if we don't do any pre-processing with 6.8 million parameters, we're going to basically memorize what the result should be. for all 434 and not be able to generalize at all what our results are. So what's done in practice is we pre-train the network. So we take our network, we train it on some big generic data set like ImageNet. So ImageNet has 1,000,000 examples with 1,000 each of 1,000 different kinds of things. So here we have like kayaks and like rodeo, 2 different kinds of dogs, a Siberian Husky and something else, and an airplane. And the idea is that most of the network basically just learns how to do image processing. So that's the light blue. And then we'll copy most of the network except for the last little bit, or anything we need for specific formatting. We'll copy all of that and then use that as an initialization to learn, for that last little bit, to learn about our specific data set. But as an initialization scheme, it works well. In the Bayesian setting, it's kind of like, this initialization is kind of like other problems where we initialize like an expectation maximization problem with a k-means, if that means anything to you. If it doesn't, that's okay. But it's really just an initialization scheme, assuming that whatever the solution is for ImageNet should be close to a good solution for OASIS. But I think that's just begging for a Bayesian interpretation. And so the Bayesian interpretation here would be, well, all of this work of pre-training on ImageNet is just defining a prior. And it's defining a like data-informed prior of what a neural network should be that does work on images. And so we apply that prior to our data set, and then we just learn a posterior distribution on that. So we, in some places, maybe we have the data to say, oh, this should actually be very different, in other places less so. But then this is just, we can apply probabilistic backpropagation here. So or any other Bayesian method, and I'll probably look at a lot of them. But in this case, we would learn means and variances for our weights based on ImageNet, and then we'd relearn them for OASIS. But we'd have a better prior, which is our subjective understanding of uncertainty in the problem, before we go into it. And I think that's potentially has a lot of use, and I think is a much more theoretically motivated understanding of transfer learning. So, to close up, so neural networks are really good at real-world problems. There's a lot of them where they're state-of-the-art, nothing comes close. But they don't typically handle uncertainty, so we need to introduce Bayesian statistics. And basically the idea for uncertainty is that that just makes our decision-making process that much better. If I know that my system is very sure and I can trust that, then I can make better decisions later on. The problem with a lot of methods is they're slow or have other problems, and probabilistic backpropagation seems to me an ideal, scalable, flexible framework for dealing with Bayesian neural networks, so we can do uncertainty, but we don't have to sacrifice on speed. And what I really want to work on is developing the Bayesian analogs for existing deep learning work. So this is the transfer learning, this is the classification, max pooling, all of these things that are really important for real-world applications. They haven't really been investigated much on the Bayesian side. And so I want for my dissertation to be about that, so that we can apply all of these, have all of these sophisticated models for predicting things based on images and other complex data like that, but have uncertainty. So, thanks for watching. If you have questions, I thought my email was on there, but my email is also on my website. And the PDF of this presentation is at that link below. I'll probably put it in the description as well. But really want to thank you for your time. That was a long talk, and not all of it was probably familiar to everybody, and so I appreciate you taking the time. Thanks.